But let's first go to the example. It's like it's a slight modification of one you should have done in recitation. I don't think I worked one of these in the lecture, but to describe it, I have to draw two views of it to make sure you know exactly what I'm talking about. So it's our old, sometimes it's called an ice cube, the two-compartment ice cube tray problem. You know, you fill an ice cube. It's a very old-fashioned type of ice cube tray, not a modern one, which is all plastic and where there's no leaking from one compartment to another. But the old kind of ice cube tray, you know, there were compartments, and these were metal separators, and you leveled the liquid because it could leak through the bottom. They didn't go right to the bottom. If you don't know what I'm talking about, it makes no difference. So I'm going to so this is the side view. This is meant to be twice as long, but to make it quite clear, I'll draw the top view of this thing. You have to imagine this is a rectangle, all the sides are parallel and everything. This is 1 and this is 2. All I'm trying to say is that the cross-sectional area of these two chambers, this one has twice the cross-sectional area of this one. So I'll write a 2 here and I'll write a 1 there. Of course, it's this hole here through which everything leaks. I'm going to let x be the height of this liquid, the water here, and y the height of the water in that chamber. Obviously, as time goes by, they both reach the same height because of somebody's law. Now, what's the system of differential equations which controls this? Well, the essential thing is the flow rate through here. So that flow rate through the hole in units, let's say in liters per second, just so you understand, I'm talking about the volume of liquid that goes through in a, I'm not talking about the velocity. That's proportional to the area of the hole, the cross section, the size of the hole. So the area of the hole, the cross-sectional area, right? And it's also times the velocity of the flow. But the velocity of the flow depends upon the pressure difference. And that pressure difference depends upon the difference in heights. All those are various people's laws. So times the height difference. And of course, you have to get the sign right. So I just point out the height difference is proportional to the pressure at the hole. And it's that pressure at the hole which determines the velocity with which the fluid flows through. So where does this all produce our equations? Well, x prime is equal to, therefore, some constant depending on the area of the hole and this constant of proportionality with the pressure and the units and everything else, times the pressure difference I'm talking about. Well, if fluid is going to flow in this direction, that must mean the height, the y height is higher than the x height. So it should be, to make x prime positive, it should be y minus x here. Now, the y prime is different because, again, the rate of fluid flow is determined. This time it will be x minus, if y prime is positive, if this is rising as it will be in this case, it's because the fluid is flowing in that direction. It's because x is higher than y. So this should be the same constant, x minus y. But notice that that's the rate at which the right-hand side is the rate at which fluid is flowing into this tank. That is not the rate at which y is changing. It's the rate at which 2y is changing. In other words, if you tell me this is rising 1 meter a second, then the actual amount of fluid that's flowing in there is 2, I don't know the units, but 2 times whatever the units should have been. 2 times square cubic meters per second. I don't know. I give up. Okay, give up on that. But anyway, it's got to be 2 here. Why isn't there a constant here? There is. It's 1. That's the one that's this one cross-section. So the area here is 1, and the area cross-sectional area here is 2. And that's the reason for the 1 here and the 2 here. Because we're interested in the amount by which the fluid is, the rate at which fluid is being added to this, which is only related to the height, the rate at which the height is rising, if you take into account the cross-sectional area. So there's the system. In order to use nothing but integers here, I'm going to take c equal to 2, so I don't have to put in halves. So the final system is x prime equals minus 2x. You got to write them in the right order, right? And y prime equals, the 2's cancel because c is 2, so now it's x minus y. So there's our system, and now the problem is I want to solve it by decoupling it. I want, in other words, to find new variables, u and v, which are better, more natural to the problem than the x and y, that are so natural to the problem that the system, the new system, will just consist of the two side-by-side equations instead of the single equation. So the question is, what should u and v be? Now, the difference between what I'm going to do now and what I'm going to do later in the period is, later in the period, I'll give you a systematic way of finding what u and v should be. Now, we're going to psych it out, psych out what they should be, in the way in which people who solve systems often do. I'm going to use the fact this is not just an abstract system of equations, it comes from some physical problem, and I ask, is there some system of variables which somehow go more deeply into the structure of this, what's going on here, than the naive variables which simply tell me how high the two tank levels are? That's the obvious thing I can see, but are there some variables which go more deeply? Now, one of them is obvious, sort of obvious, and suggested both by the form of the equation and by this business. It's simply the difference in heights is in some ways a more natural variable because that's directly related to the pressure difference, which is directly related to the velocity of flow. They will differ by just constants. So I'm going to call that the second variable, the difference in heights, let's call it. So that's x minus y. That's a very natural variable for the problem. The question is, what should the other one be? Now you sort of stare at that a while until it occurs to you that something is constant. What's constant in this problem? Well, the tank is sitting there, that's constant, but what thing which might be a variable is clearly a constant, must be a constant? It would be the total amount of water in the two tanks. These things vary, but the total amount of water stays the same because it's a homogeneous problem. No water is coming in from the outside and none is leaving the tanks through a little hole. Okay, what's the expression for the total amount of water in the tanks? X plus 2y. Therefore, that's a natural variable also. It's independent of this one. It's not a simple multiple of it. It's a really different variable. So this represents the total amount of, this variable represents the total amount of water, of liquid in the two tanks. This represents the pressure up to a constant factor. It's proportional to the pressure at the hole. Okay, now what I'm going to do is say, okay, this is my change of variables, and now let's plug in and see what happens to the system when I plug in these two variables. Now, how do I do that? Well, so I want to substitute, get the new system. The new system, or rather the old system, but in terms of what makes it new is in terms of u and v. What will that be? Well, u prime is x prime plus 2y prime. But I know what x prime plus 2y prime is because I can calculate it from this. What will it be? X prime plus 2y prime is negative 2x plus twice y prime. So it's plus 2x, that's 0. And how about these two? 2y minus twice this, because I want this plus twice that. So it's 2y minus 2y, again 0. The right-hand side becomes 0 after I calculate x prime plus 2y. So that is 0. Which is, of course, clear. Now, that makes sense, of course, because since the total amount is constant, u prime, that says that u prime is 0. Okay, what's v prime? V prime, well, that's x prime minus y prime. What's that? Well, once again, we have to calculate. It's x prime minus y prime is minus 2x minus x. That's minus 3x. And 2y minus negative y, that makes 3y, plus 3y. All right, what's the system? The system is u prime equals 0, and v prime equals minus 3 times x minus y, but x minus y is v. In other words, these new two variables decouple the system. And we got them, as scientists often do, by physical considerations. These variables go more deeply into what's going on in that system of two tanks than simply the two heights, which are too obvious as variables. All right, what's the solution? Well, the solution is u equals a constant, and v prime, and v is equal to, well, the solution to this equation is some constant, a different arbitrary constant from that one. These are side-by-side equations which have nothing whatever to do with each other, remember, times e to the minus 3t. Now, there are two options. Either one leaves the solution in terms of those new variables, saying they're more natural to the problem, but sometimes, of course, one wants the answer in terms of the old ones. If you do that, then you have to solve back. In order to save a little time, since this is purely linear algebra, I'm going to write what the, instead of taking 2 minutes to actually do the calculation in front of you, I'll just write out what the answer is. So to express in terms of u in x and y, so in other words, this is a perfectly good way to leave the answer if you're allowed to do it. But if somebody says they want the answer in terms of x and y, well, you have to give them what they're paying for. So in terms of x and y, you have first to solve those equations backwards for x and y in terms of u and v, in which case you will get x equals 1/3 u plus 2v, using the inverse matrix or just do elimination, whatever you usually like to do. And the other one will be 1/3 u minus v. And then if you then turn these, substitute in, you'll see what you'll get is 1/3 of c1. C1, u is, u is C1. Plus so, all right, C1 plus 2C2 e to the negative 3t. And this is 1/3, what is it, C1 minus C2 e to the minus 3t. And so the final solution is, in terms of the way we usually write out the answer, then x will be what? Well, it will be 1/3 C1 times the eigenvector 1, 1, plus 1/3 times C2 times the eigenvector 2, negative 1, times e to the minus 3t. So that's the solution written out in terms of x and y, either as a vector in the usual way or in terms separately in terms of x and y. But notice, in order to do that, you have to have the equations, these backwards equations. In other words, I need the equations in that form. I need the equations because they tell me what the new variables are. But I also have to have the equations the other way in order to get the solution in terms of x and y finally.